Here we are doing a little Calc 3, doing a partial derivatives preview. Well, my goal in this is to teach you a skill that you'll then eventually use, but for right now you might not understand why we're going to use it, but you're going to practice a lot of how. How. And we'll understand some why in the future. For example, here we are, partial derivatives. Now I know we have this picture, and it's debatably clear. Well, let's try this one. So what I have here is my coordinate grid. So we can see the coordinate grid. What if I place a 3D object on it? And what if I told you there was some equation that would give me the height of this irregular object dependent on its x, y location? Well, I would call that function a function of x and y, where that function of x and y outputs something, x, y, it gives me a height in the third dimension. Well, I know that, this surface is a little bit smooth, but I know the changes in this surface are not only in a single direction. The changes on this surface at any moment have to do with the change in x direction and the change in y direction. And so what we'll do is when we do a partial derivative, I just take one slice here. I'm just going to take this slice at x equals -2 and imagine what would the change be if I hold this x constant. How does the y, how does it change along this y as I hold my x constant? As I drag from top to bottom, how is my y, the derivative, the change over time, changing? And so that's what you'll see. We have some ways to write this, whether that's this partial, squiggly, backward 6 looking thing of the function with relation to x, and the function with relation to y. So, and again, like it says, we know changes in the surface, changes in the function, are not only due to a single variable, but multiple variables. So let's do some examples with this. And like it says, whenever we do these, we ignore changes due to any alternate direction, it should probably say. Because we won't just be dealing with x and y, we'll be dealing with x, y, z in terms of multivariate functions. Now, I can't give you a picture of a 4D object and describe how it might be changing in all three directions at once, but I'm going to ask you to use a little bit of imagination to get yourselves there today. Here we go. Let's do some partial derivatives, mainly practice. So again, what I could and should be doing is when I'm evaluating df dx, y gets treated as a constant. It's almost the same as if I did this. And you'll see me use this strategy, and I'll verbally use it, but I really won't use it much beyond this first example because it's technically improper math. You'll see. So this function, if I plugged in a number for y, it would turn into this. Well, let's take the derivative with respect to x. In this case, since it's dependent on x and y, I'm not taking an entire derivative, I'm just taking the partial as x changes. Well, here, this would give me a 2x times whatever this thing is, and again, that was my placeholder for y. Over here, this derivative of 3x would just be 3, and this was my placeholder for y squared. I know this is a little bit of a jump for you to take mentally, but just realize I'm never going to combine this 4 squared with 3 because y squared and 3 are not like terms. But I'm going to treat this as if it's a constant rather than a variable. Let's try it again. df dy we're going to work on, but again, what I'm going to do is I'm going to set x equal to some number. Let's choose 7. So this would be like 7 squared y plus 3 times 7 times y squared. Again, I'm never going to combine these because they're not like terms. The 7 is just like a mental placeholder as you go through. And I'll replace all those 7s with x's as I do my calculation. The derivative of y is just 1. So it's 1 times placeholder squared. Over here, the derivative of y is 2y squared is 2y, so this becomes 6 times placeholder times y. This one gets a little bit complicated. I should probably have given myself more space because I have a product rule going on. So I'm just going to do one derivative and not both. So if this is g, and I'm going to do partial g partial x, that means I need to think of, well, what is e to the xy? When I take the derivative with respect to x, well, remember, this would be like e to the power 7x. And so, yeah, the derivative I would get would be placeholder e to the power placeholder x, y e to the y x. Because y is just a constant. If this was 3x, the derivative would be 3, and I would be chain ruling it down. Since y is being held constant, it's going to chain rule down. Same idea with this one, sine x squared plus y squared. This is no different than the derivative of sine x squared plus 4. The derivative of x squared plus 4 is going to be 2x. This is a chain rule. Derivative of the outside times the derivative of the inside. Again, because this is chain rule, I needed f prime g plus g prime f, and I probably shouldn't have used g because now I'm double using it. But if I ignore the name of the function as g, this will all come together. I need this original times this derivative. It's going to be yucky. 2x e to the xy cosine x squared y squared plus my second one. And that second one, like we said, is going to be this derivative times that original. Y e to the, I'll write it more proper, xy sine x squared plus y squared. Right? It feels uncomfortable, it feels weird, but just treat it like I said. When I'm taking this derivative, I'm taking the same derivative as sine x squared plus 4. And so sometimes I mentally replace the variable I'm holding constant with a constant so I can see what it would turn out to be. Even like this one, I know the derivative of ln of something is 1 over something, and in this case I'd have to chain rule it, so it'll be times the derivative of that something. Well, I know that the derivative of this, if I did it just in terms of x, would be 2x. But then I'd have to divide by that original function. The same, because that internal derivative with partials would just be 2y and 2z. I wanted to talk about one final thing at the bottom of this page, right? We talked about that alternate formatting, h of x. Well, in the notes, or in the assignment, you'll have things that go like h of x, y. This means take that derivative h of x and do a partial based on y next. Yeah, we'll do a partial based on y next. So, again, what you could be thinking is if I needed to take the partial based on y next, this would be like some constant, but in my denominator, it would be like, again, 4 plus y squared. And that's kind of like 4 plus y squared to the negative 1 power. So I would get negative 1 times that numerator constant, and then I would power rule this thing down to a x squared plus y squared plus z squared to the power negative 2. I know it feels weird, I know it feels yucky, I know it's definitely challenging, but, ooh, and I forgot to chain it. Times 2y, my bad. So, I didn't mean to drag us into a bad example. I meant to show us, hey, if it has h sub xy, I need to do h sub x and then take another partial based on y next. And I know it feels weird to hold y constant and take the derivative of x, then hold x constant and do the derivative of y, but that's what the instruction says. Now we flip to the back page, and here you just see where. Where am I going to use this skill? Again, we don't exactly know why yet. We don't know exactly what these symbols and things imply, but we can know how, and I can show you a little bit of where before we get there. That way, when we get to this lesson, these lessons where we're finding tangent planes, critical points, directional derivatives, gradients of functions, it's not so bad because you've already practiced the skill. Here we go. When finding a tangent plane of the surface, we use the partial derivative. First, I find the partial derivatives. Well, again, this would be like x squared plus 4. My derivative here would just be 2x. My derivative here would be like 4 plus y squared. That derivative would be y. So then I'd evaluate this derivative at this point, and it would begin to give me the change based on x and y at this coordinate 1, 2, 5. Again, we'll see how that plays out in a future lesson, but realize if I want to find a tangent and I have some surface, and I want to find a flat tangent, I need to see how x and y are changing at every given moment. When we are finding the critical points of a function, as I move my paper, we find the partial derivative. So first, we find some partial derivatives. Partial derivative of this one would be 3x squared. Partial derivative of this thing would be negative 3. My linear x drops off, but that y squared stays. And this y cubed is just a constant because I'm just doing a partial based on x. So it's done. Repeat again with y. X is now the constant. Gone. This becomes negative 6 from that power rule, xy. And this becomes 3y squared. Now, I would set the partial derivatives equal to 0 to find the critical points, and then I would find the xy coordinates that satisfy this equation. I wonder what that means x and y might be equal to. I wonder what this means x and y would be equal to. And then the magic of calculus takes you away in chapter 14. Here we are still, not there yet, just showing you where. A directional derivative. This is like walking down a steep slope and I'm trying to decide what direction am I going to put my foot in. In this case, I'm going to put my foot that direction. And I want to see, how does the slope change? How does that surface change when I'm pointing my foot that direction, that specific direction? Well, I would have to know how it changes based on x, and I would have to know how it changes based on y. So I take my directional derivative of the function. A little chain rule here. Again, this is no different than how I would take this derivative, but I just know this is a placeholder. And I'd see a repeat over here. I use that symmetry on these examples just to keep it simple. Well, what makes up the x component of a vector? What would make the y component of this vector? I wonder how I could take sine and cosine of a certain vector and then apply it to my directions at a specific coordinate xy. Last but not least, a gradient. This gradient is so important. We will be using this all the way to the end of the year. We'll even take the gradient and cross it with a force field. How is the surface changing crossed with how the forces around the surface change? Don't forget, I might integrate that and add up all of those little calculations at all of these little moments. But enough scary stuff. Let's just do some partials. This partial based in x, this would make 2x. and I bring that constant y along for the ride. Y, z has no x's in it. It's a constant. It's gone. Z squared x is linear, so this just drops to a z squared. Here again, linear y drops to a plane x squared. Y squared becomes 2y. Bring along that constant z, and no y term is a constant. It's gone. This should say f sub z, where I'd get nothing, y squared, and 2zx. Hopefully you see by the end that this is not so scary. It's taking derivatives. You just have to kind of wrap your mind around holding one thing as a constant. It's not implicit. You have to understand it's not quite implicit differentiation. It's just a little bit different. And now I would take my x, y, and z directions of change and put them into a vector of change. I'll leave you thinking there. Happy day.